In this module, you will learn about the solubility equilibria of sparingly soluble salts. We have learned in the previous classes that the maximum amount of the solute that dissolves in 100 ml of the solvent at a given temperature and pressure is called solubility. These 4 beakers contain 100 milliliters of water each. In each of the beakers, 3 grams of different salts, sodium chloride, lithium fluoride, magnesium chloride, and barium sulfate are dissolved and stirred. What do you expect to happen? You observe that the salt in the beakers containing the solutions of sodium chloride and magnesium chloride dissolve completely, while the other 2 beakers still contain large amount of undissolved salt. From this, we can conclude that all the salts are not soluble in water to the same extent. Salts like lithium fluoride or barium sulfate, which show little solubility in water, are commonly termed as sparingly soluble salts. Do you know why all the salts are not soluble to the same extent in water? Let us try to understand this. The ions in an ionic solid are held together by strong electrostatic forces of attraction. For its dissolution in the solvent, energy is required to overcome the attractive forces between the ions. This energy is called the lattice enthalpy. Let us once again recap the definition of lattice enthalpy that we have already learnt. The lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into its constituent ions. When such an ionic solid is dissolved in a solvent, certain amount of energy is released. The amount of energy released when 1 mole of a solid salt is dissolved in a solvent is called the solvation enthalpy. In other words, the energy released during ion-solvent interactions or in the process of solvation is called solvation enthalpy. A salt is soluble in a solvent only when the solvation enthalpy is higher than the lattice enthalpy of the salt. That is, the solubility of a salt depends on the amount of solvation enthalpy, which in turn depends on the nature of the solvent. For example, sodium chloride is highly soluble in polar solvent, water, because the solvation enthalpy of water is sufficiently high enough to overcome the lattice enthalpy of the sodium chloride salt. On the contrary, you can observe that sodium chloride does not dissolve in kerosene or benzene. Kerosene and benzene are non-polar solvents. Their solvation enthalpy is small and not sufficient enough to overcome the lattice enthalpy of the salt. Hence, salts do not dissolve in non-polar solvents. We are familiar to the fact that each salt has its characteristic solubility at a given temperature. Depending on the extent of solubility, salts are classified into 3 categories. Salts with solubility greater than 0.1 moles per liter are considered to be soluble. Salts with solubility between 0.01 moles and 0.1 moles per liter are considered to be slightly soluble. And Salts with solubility less than 0.01 moles per liter are considered to be sparingly soluble. Now let us discuss the solubility equilibria of sparingly soluble salts, such as silver chloride. Silver chloride is a sparingly soluble salt. When it is added to water, only a small amount of it goes into the solution, and a stage is reached at which the dissolved and undissolved silver chloride are at equilibrium. That is, a saturated solution of silver chloride is said to be formed. Thus, a dynamic equilibrium is set up between the undissolved solid and the ions in the saturated solution, which can be represented by the equation as shown here. The equilibrium constant for this equilibrium can be written as K equal to the product of concentrations of silver ion and chloride ion divided by the concentration of silver chloride. You have learned that the concentration of solids and liquids are not included in the expression for equilibrium constant because their concentrations will remain constant. As the concentration of silver chloride remains constant, the product of K and the concentration of silver chloride in the equation is represented by another constant called Ksp, which is the solubility product constant or simply the solubility product. Thus, the above equation deduces to Ksp equal to the product of concentration of silver ion and chloride ion respectively. The experimental value of Ksp for silver chloride at 298 Kelvin is equal to 1.8 multiplied by 10 to the power of minus 10. This means that in a saturated solution of silver chloride, the product of the concentration of silver ions and chloride ions is equal to the solubility product Ksp of silver chloride. The solubility product of a sparingly soluble salt at a given temperature may be defined as the product of the concentrations of its ions in the saturated solution, with the concentration terms of each ion raised to the power equal to the number of times the ion occurs in the equation representing the dissociation of the salt. Mathematically, we can write Ksp expressions using molar solubility, S, in place of individual ion concentrations. Note that molar solubility is the number of moles of the substance present in 1 liter of the solution. If we define S mole per liter as the molar solubility of silver chloride, then S moles of this salt dissolve in 1 liter of solution. In a saturated solution of pure silver chloride, the concentration of silver ions is equal to the concentration of chloride ions, which is equal to S mole per liter. Substituting S instead of concentrations in the expression for solubility product gives Ksp is equal to S multiplied by S, which is equal to 1.8 into 10 to the power of minus 10. Thus, the molar solubility S is equal to square root of 1.8 multiplied by 10 to the power of minus 10. This is equal to 1.34 multiplied by 10 to the power of minus 5 moles per liter. Thus, the solubility of 1 mole of silver chloride in 1 liter of solution is equal to 1.34 multiplied by 10 to the power of minus 5. The expression for solubility product may be written as Ksp equal to the product of the concentrations of the ions involved in the equilibrium, each raised to the power of the coefficient in the equilibrium equation. For example, consider a generic salt of type AX2. The equilibrium reaction for this dissociation may be represented as AX2 in equilibrium with A plus 2 and 2X minus. The solubility product, KSP, for the salt AX2 can be written as KSP is equal to the product of concentration of A plus 2 and X minus raised to the power of 2. A salt may give 2 or more than 2 cations and anions when dissolved in water. For example, consider the salt calcium phosphate. When calcium phosphate is dissolved in water, it dissociates into 3 calcium ions and 2 phosphate ions. The solubility product, KSP, of calcium phosphate is equal to the product of the concentration of Ca plus 2 raised to the power of 3 and the concentration of PO4 minus 3 raised to the power of 2. If S is the molar solubility of calcium phosphate, then the concentration of Ca plus 2 ions will be equal to 3S and the concentration of phosphate ions will be equal to 2S. Substituting the concentration of calcium and phosphate ions in the KSP equation for calcium phosphate, we get the solubility product KSP is equal to the product of 3S raised to the power of 3 and 2S raised to the power of 2. This is equal to 27S cube multiplied by 4S square. The product of this is equal to 108 multiplied by S raised to the power of 5. Thus, the solubility product of calcium phosphate is equal to 108 multiplied by S raised to the power of 5. If the solubility product, KSP, of the salt is known, then the solubility of calcium phosphate is equal to 1.05 multiplied by 10 raised to the power of minus 5 mole per liter as shown. You have now reached the end of this module. In this module, you learned that the energy required to overcome the attractive forces between the ions in a solution is called the lattice enthalpy. The energy released during the process of solvation is known as solvation enthalpy. A salt is soluble in a solvent only when its solvation enthalpy is higher than its lattice enthalpy. Depending on their solubility, salts are classified as soluble, slightly soluble, and sparingly soluble. The solubility product of a sparingly soluble salt at a given temperature may be defined as the product of the concentrations of its ions in a saturated solution with the concentration terms of each ion raised to the power equal to the number of times that the ion occurs in the equation representing the dissociation of the salt.